Okay, hi. We'd like to just list a few properties and show how to prove them. Maybe with some examples too. So let's see. One, P of EC is 1 minus P of E. And that's clear because I won't even write it. We did this actually in the last lecture. EC union E is S, right? So if I added the e to the other side, p of e to both sides, I find that I have p of s equals 1. So I can start there. So for example, I could do a little example of this. If e is equal to the sum of two dice is greater than or equal to 10, we found that was equal to 6 over 36, or 1/6. So that implies probability sum is less than or equal to 9 is equal to, so P of E was equal to 1/6, and that implies this is equal to 5/6. Okay, so often if you know one already, you can find the probability of the complement, or one's easier to find. And then you can find the probability of the complement by just subtracting from 1. 2, if E is contained in F, possibly equal to F, then what do you think? P of E should be less than or equal to P of F. This is clear from some examples. Suppose E is above, E is the sum, two dice are greater than. So let E be as above. Suppose F is, say, equal to the sum, two dice greater than or equal to 8. So that E is contained in F, right? Because if it's greater than or equal to 10, then it's greater than or equal to F, 8. And you can see P of E, again, is a sixth. And P of F, well, let's see. It contains all those that are greater than or equal to 10. Then all the ones equal to 9. There are 4 cases that are equal to 9. 6, 3, 3, 6, 5, 4, 4, 5. So it contains an additional 4. So already we see it. And then 8 is an additional 5. So it's an additional 9. So this is actually 15 out of 36. Or, yeah. Let's see, 5 out of 18. 3 out of 18, 5 out of 18. So, okay. 3. Probability of E union F is equal to probability E plus probability F minus probability EF. Okay, if I was going to do, let's see, there's a special case sort of here. So let's have, well, you can do this for yourself with one, I think. Let's prove. We'll look at this a little more closely in a second. Let's prove 2. So E is contained in F, right? E is contained in F. So here's the idea. I have F here as some event, and E is contained inside it. The way I can think about this is even these are maybe outcomes. So E contains all the outcomes also in F. Maybe the outcomes are little regions in here. Anyway, the picture is just meant to be get you thinking on the right way. So E and then F, and E is contained in F. So probably the simplest thing usually with a lot of these is to make a decomposition of the largest event in terms of other events that are mutually exclusive. So we can say F, we know, is equal to E union. Now what set is mutually exclusive with E that will create F? Well, it's everything outside of E, right? So that I can call F intersection EC. Oh, now these are mutually exclusive. So I know the probability of F is equal to this, is equal to the probability of this union, but they're mutually exclusive. So I'm using axiom 3 there. Okay, but this is greater than 0, right? This is greater than or equal to 0. So since, okay, we have P of F must be greater than or equal to P of E. Probabilities can't be negative, otherwise it wouldn't prove it. But you know this is not less than 0, so F must be greater than or equal to P of E. All right, for 3, we're going to prove 3 in a more general way in a second now. So let's see. And maybe just an example. So for 3, say an example of 3. Suppose again E is some greater than or equal to 10, 2 dice. So that's 6 of them, right? And let's let F be, say this time, doubles. All right, well then, if I make my picture here, we know we have this is the union here. That's E. And then F is all the diagonal. Okay, yeah, right. All the diagonals. Okay, so the union, probability of the union is, let's see, 10 out of 36, right? So P of, but let's check. P of E, 6 out of 36. P of F, all the doubles, also 6 out of 36. P of EF, well, that's just equal to the probability of being in both. So let's see, that's 5, 5, and 6, 6, which is 2 out of 36. And then, sure enough, we get P, E union F equals 6 plus 6 minus 2 over 36, 10 over 36. Which is right? It's just everything in here and here. So that's 10 of those. All right, so let's do a proof of, we'll do a proof for the general case, which follows. Let me just write the general case down for 3. There is this, we can put this 4, and this is called the inclusion-exclusion principle. Okay, which says the probability of the union of n events. Not necessarily mutually exclusive. We know if they're mutually exclusive, it's just the sum from axiom 3, but so they can overlap. Well, this is computed this way. First, I take the sum of each of them, each event, and then I subtract off from it all the intersections of size 2. So I subtract off, I start with indices like this. Let's say I1, I2 less than n, P, E, I1, E, I2. Okay, so I'm picking different indices. Obviously, I don't want to pick two of the same thing and take the intersection. That doesn't make any sense. So I am taking all the different pair combinations of it, so that I am taking that and subtracting that now. And now I'm adding back in the next one. So then I add back in the 3's. Okay, you want me to write this? I don't know. So I don't think I'll write the 3's. Let's go right to the r's. So I will have -1 if r is even. I want the sign to be negative. There's 2 of them. So it's -1, it was positive. 3 would be positive. So here I want r plus 1, summation 1, I1, I2, IR, less than or equal to n. And here I have P, EI1, EIR. The reason we can't just write E1 through ER is because those subscripts represent certain events, and this means take all possible intersections where I have an index here, it's bigger than or equal to 1, another index bigger than it, etc., like that. So that's what that notation means. It just means all possible intersections of size r. Okay, I have to keep going. And finally, the last one. The last intersection, though, is just one term. So it's -1 to the n plus 1. And here I just write p. And I can go back to the constant subscripts here because there's only one term. So I know what they are. All right. We have to stop in a second. So this is the formula. I add in, I take out, I add in, I take out of all the different sizes. And this should end up giving me the same probability on the left and the right. All right, on the next video, I will do proof of this.